Hello and welcome back. Firstly, again, thank you very much for all your comments, feedbacks and views of the last video. As ever, I'm still surprised by the overwhelming positive response, so thank you for that. In this video, as I said when we left off the last, it concentrates mainly on just drilling the oilways in the flywheel. It's actually going to be quite a long amount of work, and I'll do my best to speed it up where possible, where it's repetitive, and cut out what's necessary, but I still hope you find it interesting. If there's time at the end, I will do some measurement work gathering data for the manufacture of the timing side main shaft. Thanks very much, hope you enjoy. Hello again. So here we are about to actually start cutting metal to drill the first of these oilways. First job is to create a little flat surface, little counter bore to give us a flat surface to work on, and this will also end up being the counter bore that the head of the sump sludge trap will sit in. So let's get going. Just got down to a complete diameter on the counter bore. I'm going to zero this clock and then go down another 3mm to allow for the head of the sludge trap cover. And there we go. 3mm. Just zoom you in slightly. There we go. So next I'll get a centre drill up and we'll get a centre mark ready to actually start drilling. Right, that's the centre point done. Let's get the first of the long series drills in there. Right, we're ready to start drilling. Let's see how this behaves. This is the easy bit, and the hole's not very deep. The secret to this deep hole drilling is to keep clearing the swarf at the bottom of the drill, bringing the drill up and making sure the flutes stay clear and you use plenty of cutting oil. Otherwise you'll get a build up of swarf jammed in the bottom of the flutes and you risk snapping the drill. I'm now at the point where I've virtually used all the travel of the machine and I have to wind the bed up a little to continue going deeper. Before I carry on drilling, just show you something I'm about to add to the setup. When this drill breaks through to the big end bore, it's going to come through roughly half and half into the bore, which is why I want to help with the oil feeding and aligning up with holes in the big end pin, but it's not good for the drill to half and half break out into a hole like that. It may try and snatch, and again I don't want to risk breaking things. So I've just made a little plug to fit in there, which will fit in there when I get it straight. That's better. And so the drill's gonna be supported on both sides when it breaks through. So I'm just going to add this to the setup here. Right, that's in tight enough, so I'll carry on drilling. Last cuts, I've now haven't got enough travel on the quill of the mill to completely disengage the drill, and having wind the whole table down, then back up, and drill a little more. And that's as far as we can go. So you have to drop the drill down there to get it out at the moment. What we can do is move along. Drop it back in to where I had it. And have a look to see roughly how deep we actually got. Which is just about halfway into the bore. Ideally if we could get a couple more mil on that. Just put a mark on the drill. See if I'll pull that out a little bit more, just to go that tiny bit more. Put that back in the hole. Come back to 0. Back in the chuck, just see if I can get a tiny bit more on that. Not very good, just hold on the very end of the drill, but I'll just back and get away with it. Yeah, that will give us about another 4 or 5 mil. And there we go. That's brilliant. The drill did behave itself very well there. As I think I said earlier, high cobalt HSS made by Osborne, a good make of tools, and that has worked very well. I am pleased with that. So let's just undo that little plug that I put in down the bottom here, and we should see the drill half breaking into the big end bore. Do that from either side. There we go. And what you can see, hopefully there, is half the hole out the plug, and the other half is nicely in the big end bore. So that's brilliant. Well pleased with that. We'll look to opening out and tapping the hole just for the sludge trap plug, and then we can think about setting up to drill the second hole, which is luckily not as deep as that, so it won't be so much work. Next operation is to open out the top of that 4mm hole and drill it out to a suitable size to tap the 5/16 UNF thread that we're going to do. So let's use a 6.9mm drill. And we'll 0 on top there. There we go there, much easier than the 4mm hole. And we'll get a 5/16 UNF tap and get that thread started. Just going to run a finishing tap down there now we've started the thread. cut in nicely enough. Nearly there. That'll do us. That's looking nice. Now we've completed this first oilway, we need to drill the second, and the second one is actually in line with the main shaft axis, so we need to move 15mm back that way, as we pitched over off centre line 15mm to do this one, and the second hole is at an angle of 45 degrees to intersect with this first hole. Remember our drawing, so we've just drilled this hole here at 9 degrees and we want to come round to 45 degrees. So let's get that pitched over, back that 15mm and move round to 45 degrees. Undo the slideway clamps. And over 15mm. Just lock the slideway clamps up again. Right, I now need to index round 45 degrees. 1, 2, 3, 4, 5. That's 9 degrees of revolution, 5 9's 45. So I now should be in exactly the right position to drill my next hole. It will bisect this one coming across and go down to the main shaft. So it's just now a repeat of spot face, centre drill, drill, as we did before. That's the oilway drilling done. You can see hopefully the two drilled and tapped holes at the top there. If you look here, we've got this one, which is this bore here, going to the centre main shaft. Then we've got this one coming up, bisecting the first drilling and coming up to the big end, and hopefully you can see, oh, quite heavy, the drill just showing there. So I'm chuffed with the way that went, and we can look to get on with the next bit on the crankshaft assembly, which is starting to think about making the timing side shaft, modifying the drive side shaft, and also just start thinking about the amount of material we need to move to get the necessary balance factor, which will be some material taken away in this area. That's the oilway drilling done. You can see hopefully the two drilled and tapped holes at the top there. If you look here, we've got this one, which is this bore here, going to the centre main shaft. Then we've got this one coming up, bisecting the first drilling and coming up to the big end, and hopefully you can see, oh, quite heavy, the drill just showing there. So I'm chuffed with the way that went, and we can look to get on with the next bit on the crankshaft assembly, which is starting to think about making the timing side shaft, modifying the drive side shaft, and also just start thinking about the amount of material we need to move to get the necessary balance factor, which will be some material taken away in this area. This morning I want to start gathering details to be able to make the new stub shaft that's elongated to hold the ignition rotor. So first thing I want to do is just record the necessary dimension. So I have done a quick little sketch, hopefully you can see that, and I'll start filling in the dimension. To get all the relative lengths, I'll use this height gauge. I have just cleaned up the surface table, checked we zero nicely, so I can start picking up dimensions. Get me pen and paper ready, and here we go. Hopefully I'm not too in the way, but get this little flange dimension down here, and I have got 75, 85, 88 thou. I will also do is a quick vernier check just to make sure I have not slipped a rotation of the thimble on the height gauge. And actually, now I've just cleaned that up a bit, we're actually near 75, 80, 83 thou. Jot that down, and I can go up to the next step. Oh, we're going to have to go up. This height gauge increments up in inch divisions, slightly unusual design, and then you use the micrometer thimble to fine adjust. So I've got that at 1 inch, 1.8125, which sounds like an inch and so many sixteenths. Again, quick check with the vernier, and yes, I'm getting 8.10 with that. So And now I'm close enough. Go up to the next step. Have to index up another inch. That's there. And come down 2.682. 2.682. Here's again, quick check with vernier. And I'm getting, oh, slipped, 2.688. So yep, same ball court as well. Then finally, let's go to the top. Looks like may just need to, yep, got to go up another division. And then wind the thimble all the way down. And we've got, 3 inches and 2.5 thou. Again, out with the vernier again. 3 inches and 5 thou. So we're fairly consistent. 3.0025. So that's the lengths. So look at the diameters. Check I zeroed the micrometer. And here I've got a metric micrometer and we did the length in heights, but I can sort all that out on the drawing. So we have got 19.980. That's on the interference fit with the flywheel. We've got the part that runs through the oil feed area, and that is still the same, 19.980. I can see we're a bit worn here where you've got the little groove the oil's fed into either side of that. If I go on the high point, the not worn side, still 19.980. So we're pretty good on that. Then we've got the diameter, the skew gear and timing gear sit on, which is a light interference, and we have got 15.88. 15.88. Maybe a gnat's under that. This micrometer has got a vernier as well. So 15.877, something like that. Jot that down. This wants to be fairly good because you don't want these gears to be loose. But again, you don't want too tight a transition fit because they're pretty awkward to get on and off. Then finally, the threaded end, I'm not going to replicate that particular thread, so I will just choose a thread that suits that, but we've got the extended amount to go on, which I'll work out from the rotor. Oh, nearly missed out one feature. This interesting Triumph feature we have here, that on the outside of this flange, which I need to record the diameter, it's, well, either straight knurled or you might call it a fine spline, and actually Triumph drive this outer diameter into the flywheel. I don't know if you can see this here, but it actually, the shaft broaches into the flywheel here, which is a bit of a Triumph bodge to try and I presume stop these shafts rotating. I'm not going to try and replicate this on this timing side. The load is pretty light on that, and I'm fairly confident in the force fits I'll have on, or shrink fit I'm going to have on these diameters here to do that. But I will try and replicate that when you come to the drive side. I don't think it's a very clever design, because as you broach in this spline, you can actually see it generates little bits of swarf that gets pushed into the counterbore. So how well this shaft bottoms out, I don't really know. I can see it appears that there's a little tiny little face groove here, which is probably intended to take the swarf generated by that broaching operation. Not a very clever design feature. On C15s and other engines, they actually mill out a square slot and have a square flange on the end of the drive shaft. I'd be tempted to replicate that, but I don't think it's necessary on this side. On the drive side, because I don't really want to have to cut this spline, I'm going to use modify an existing shaft, and to try and square off the sides and make a slot, you're not going to end up with much flange left if I try and do that. So I'm going to use this splined feature, which, as I say, I think is a little bit of a triumph bodge in the design of the engine. Having done all the diameters and the lengths, all I need to do now is just pick up these hole positions of these feed holes and the outlet hole here. So I'll grab an appropriate sized drill and put it in the hole. That's a nice snug fit, so that's really good. And just get that on the surface table and bring, if you can see that, the height gauge down onto the drill. That's about it, and then I can basically grab that reading and take half the drill off to get the centre. Then I'll repeat the same process down here for the larger hole. Last bit to measure on this shaft is just the dimensions of this key slot here, which is orientated in line with the main oil hole, the pickup holes, and this scalloped cutout. So I'm going to do this, measuring the width of this with slip gauges. For those that haven't seen slip gauges before, these are precision ground blocks that you can work up in increments of 1/10,000th of an inch, 1,000th of an inch, and then as you build up larger distances, the blocks get larger graduations. But for this, I know I'm in the region of 150 thou wide. So if I pull out a 50 thou slip and 100 thou slip, and we can just literally try them in the slot. And what I can see, that's a little bit loose. So I'll work up in a couple of thousandths. So we'll go to 102 plus 50, so that's 152. Getting tighter but still a bit loose. So let's try a couple more thou. Go up to 104. Sorry, 154. And that's reasonably snug, still slightly loose, so we'll go up one more. So that's 150 thou, and now that is just entering the slot, struggling a tiny bit at the front here, probably because there's a bit of a burr on it. Yes, there is, but it's dropping down that end and it's dropping down in there. So that's 155 thou width of slot. Just jot that down. Similarly, we can do a quick cross check with the gears. Just try and drop those same slips in, and again that just goes, no real play or rock. So that's again good on that. This one's sitting nicely apart from, there must be a little burr at the front there stopping. So that's the width of the slot. Obviously I can just vernier the length, and the last thing is to get the depth, which I'll use a micrometer plus a known packing piece to do that. So just to do this depth, I'm going to use one of my slip gauges on its side, 150 thou wide one, so it sits nicely in the slot, and then I can take a micrometer across there, take a measurement and subtract the width of the slip gauge. So that's 22.96, and the slip gauge measures 7.9 millimeters. So I can subtract those, and I get a dimension from the underside of the shaft to the bottom of the slot, which is not a bad way of dimensioning something like that, because when I actually get to machine that, I can use the same measuring method to check I've got the right depth. From all that measurement work, I've now produced a model and CAD drawing, so we can think about machining. I hope you enjoyed that, and look forward to any comments and feedback you've got, which is always very welcome. On the next video I will either be starting manufacture of that timing side main shaft if the material comes through in time, or if it doesn't, I've got a couple of sets of crankcases where I want to machine a sprocket access hole behind the clutch, so I could perhaps fill in with that. We'll see how we get on. So again, thank you very much, and I look forward to producing the next video for you. Thank you.